So Gibson here. We're going to move ahead in this lesson and look at electric fields. We've studied electric charge and the forces between them. Now let's take a look at something called an electric field that gets generated by charged objects. So we're going to be able to define an electric field, solve problems related to charge, electric field strength, and forces. And also, how do we diagram electric field lines? How do we represent what the electric fields look like when we have charged objects? And then the last thing, we're going to take a little detour here and have some fun looking at the physics behind lightning. So let's first talk about an electric field. What is an electric field? Well, like gravity, electric force is a field force. No contact is required for the force to act on an object. So if we were to take a charged rod here that has extra electrons, so negatively charged, and bring it up next to an object that is neutrally charged, right? We have an even number of positive and negative charges. You notice we get a redistribution of the charges on the neutral object. Since like charges repel, the electrons, if this is a conductor, are going to easily move to the opposite side, leaving a net positive charge near the wand. Now, we've done that without actually touching them together, right? So how does that electric force get exerted across that empty space? Well, in order for the charged rod to exert a force on the sphere, it must change the property of the space around it itself. And we call that property of the space an electric field. So just like gravity, it's invisible, but we can see the effects of it. So let's define. Electric field is a force field that exists around any charged object. Its force can do work and transfer energy from the field to another charged object. An electric field is a vector quantity. It has both magnitude and direction, just like gravitational forces. Now, how do we measure an electric field or its field strength? So we're going to take a negative charged object represented by the blue circle here, and we're going to place a small positive, what we call test charge, at a location. Now, we're going to note that there would be an attractive force, right? Because we have opposite charges. The object is charged negative and our test charge is charged positive. So if we create a force, right, on that test charge, we know that there's an electric field at that location. Okay. So the strength of the electric field is equal to the force on the positive test charge divided by the amount of charge of the test charge. Okay, so we're kind of normalizing out the charge that's in the test charge, the positive Q here in our picture. So we have an equation that says E stands for electric field strength, equals the force of the charge big Q on our test charge little q. And then divide that by the charge on the test charge, the little q. Now, what is the force of our negative charge on the positive test charge? Well, that's where Coulomb's law comes in, right? We have our constant K times the two charges here divided by the distance squared between them. So if we take that and substitute that in for the force, right, we get this expression. But notice we now have the small q in both the numerator and the denominator. So those are going to cancel out, and we're left with an expression that doesn't utilize the charge of the test charge. It only takes into account the charge of the object that's creating the electric field, the object whose electric field strength we are trying to measure. So here's the way we calculate electric field strength. E equals our constant K, that's 9 times 10 to the 9th, times our charge in coulombs of the object that's creating the electric field divided by the distance squared. How far are we removed from the charge? And the units here are going to be newtons per coulomb. All right, let's look at an example where we'll calculate the field strength. It says, what is the electric field strength of a point that is 0.3 meters to the right of a small sphere with a charge of -4 × 10⁻⁶ coulombs? We want to find both the magnitude and the direction. So our big Q, the charge is a -4 × 10⁻⁶ coulombs. Right? We would put our test charge 0.3 meters away. So we're trying to figure out what is the field strength at that location. So we plug into our equation, our values for K, for the big Q, and the distance squared, and we get -4 × 10⁵ newtons per coulomb. Okay, so think about the units for the electric field strength, right? It says how many newtons of force we would have for each coulomb of charge in our blue object here. Now, we don't have anywhere near 1 coulomb of charge. If we did, though, we would have an extremely strong electric field. Because remember, how many electrons or charge or coulombs is a very large amount of charge. Now, what about the direction? Well, here's a hint. The electric field vector is in the same direction as the force vector. So the force of Q on our test charge is an attractive charge, right? So it would be to the left. The electric field strength direction would be back towards the blue negatively charged object. All right, how do we picture an electric field? So there's some rules for how we can draw these lines to model what the field strength looks like and also the direction. So the first is that electric field lines always extend out of a positive charge and into a negatively charged object. So here's what it would look like. If we had a single positive charge, the electric field lines would be drawn outward. The negative charge, the field lines will be drawn into the charge. The second rule is the electric field lines will never cross each other. The third rule is electric field lines are most dense around objects with the greatest amount of charge. Okay, so the greater the charge, the closer the field lines are to each other. Remember, we're looking at field strength or intensity. So to represent a stronger field, we would draw the electric field lines closer to each other. Now, A and B are kind of a uniform electric field, and there are ways to generate that. But you can see A would be weaker because the lines are spaced further apart. C and D, first you notice that as you move away from the charge, whether it's the weak or the strong one, the spacing between the lines gets larger, right? So that's the inverse square property that we see in the formula, 1/d². But in this case, D has a stronger field. The lines are closer together at the same distance from the charge, so we can conclude that D would have greater positive charge than C. And then the last rule is that at locations where electric field lines meet the surface of the object, the lines are drawn perpendicular to the surface. So if it's a circle, they're all going to be radially outward. But if we have a rectangular shape, the straight parts, right, they'll be perpendicular, and then the round parts, there again, they'll be drawn radially towards the center of that radius of the circle. So those are the 4 rules for how we would construct field lines. So let's look at some examples, right? We've got a positive and negative charge. Remember, the charges or the field lines are always drawn out of the positive charge and into the negative charge. So you can see the field strengths are the greatest, closest to the charges. And then you can see how the lines get further apart as we move away from the charges. How about 2 positive charges? Well, the lines have to go out of both, right? And they're not going to cross. So we get a field strength that looks like this. And the field strength right in the center of those 2 charges would essentially be 0, because we have 2 like charges. If they're both positive or both negatives, if we're halfway in between, the electric fields would basically cancel each other out. Same magnitude, but opposite directions. All right, let's look at a diagram of field strength here, and we have 3 points, A, B, and C. Let's see if we can figure out which location would have the least field strength. Okay, where do we have the least field strength? So if you said C, that's correct. C has the least because notice how far apart the lines are spaced. A has the greatest field strength because you notice it's much closer. The lines are much closer to each other than what B or C is. So this is how we model and represent fields. Now, these pictures all show a two-dimensional view of the field strength. In reality, they are a three-dimensional view. If you looked at the very beginning of the lesson, the first slide here, you saw a three-dimensional animation of what the field strengths would look like. All right, last topic here, lightning. How does lightning work? Well, static charge builds up in the clouds, and the charges are polarized in the clouds, meaning positive charges form or collect at the top of the cloud, and negative charges collect at the bottom of the cloud. And to be honest, scientists really don't understand why those charges are polarized like that. There's a lot of mysteries yet in lightning. So the cloud's electric field induces a positive charge on the surface of the Earth. Okay, so remember that rod we brought near the charged or the neutral sphere, the negative charges moved away, the positive charges moved towards it. So the same thing happens here. It kind of pushes the free electrons down into the Earth further away. So the objects on the surface of the Earth are left with a net positive charge. Now, when that situation is set up, a lightning bolt begins with the development of what they call a stepped leader. Now, the stepped leader comes down from the cloud searching, trying to find a path for those electrons to discharge to the Earth. And it will find what they call an upward rising positive charge known as a streamer, and it approaches the step leader and they meet in the air above the surface of the Earth. Most of the time you think of lightning as going from the cloud down to the ground, but initially it actually starts with a stream going up towards the cloud until the connection is made. And in a minute we'll see some high-speed videos that you can see what that actually looks like.
Lightning will strike anything that stands high above the ground. Trees are a favorite target. Lightning runs through the tree's sap, instantly vaporizing. A strip of bark can explode like wooden shrapnel and travel outward at lethal speeds. Even know what guides lightning's jagged path, or why it chooses to strike in one place rather than another. All we do know is that the path is first created by a trickle of electricity that rushes outward from a charged region high inside the cloud. It begins as a small spark inside the cloud 5 miles up. A spurt of electrons rushes outward, travels 100 meters, then stops and pools for a few millionths of a second. Then the stream lurches off in a different direction, pools again and again. Often the stream branches and splits. This is not a lightning bolt yet. It's called a stepped leader, an intensely charged channel leaping and branching down. As it gets close, its electric field begins to exert a pull on the ground.
When that step leader is within 10 or 100 meters of the ground is now aware of there being a big surplus of negative electricity, which has come down on a conductor. Certain objects on the Earth respond by launching little streamers up toward the step leader. Weakly luminous plasma filaments, which are trying to connect with what's coming down. If you happen to be standing there, maybe a streamer is going to leave your head and head toward that step leader. A telephone pole might launch a positive streamer. A blade of grass might launch a positive streamer up toward the step leader. It's that special one which makes the connection, which gives rise to the return stroke, and then this catastrophic 10,000 ampere current flows. That closes the switch.
When that connection is made, the electrons drain to Earth in a blinding bolt of light. The part of the channel nearest the ground will drain first, then successively higher parts, and finally the charge from the cloud itself. So the visible lightning bolt moves up from ground to cloud as the massive electric currents flow down. These positive streamers only exist for a minute fraction of a second. Photographs of them are extremely rare. Here, 2 streamers left the treetop, but only one of them successfully connected with the descending stepped leader. A nearby telephone pole also launched a positive streamer upward, a failed lightning bolt. For decades, ordinary pilots have also reported seeing brief flashes in the sky above storms. Their reports were ignored. But perhaps they were true. This research footage was taken above the massive lightning storms of the American prairies. Scientists have nicknamed these flashes sprites. They're almost too faint to be visible and last a fraction of a second. They're 10 miles wide and reach over 50 miles straight up from the top of the storm. Nobody yet knows what they are or how the storm creates them. Their power and their effect on the atmosphere are still mysteries. But you need to go higher than a plane can fly before you can appreciate the real scale of lightning on Earth. Images from a low light level camera on the space shuttle show nighttime storms flickering across entire continents.
So here's an interesting question. What happens when you get struck by lightning? Do you die? Well, sometimes people do, but actually most people that get struck by lightning survive.
Lightning strikes someplace on Earth about 100 times every second. That's 3 billion times a year. Considering that, your chances of being struck are actually amazingly low. So here in the US, where we have pretty good statistics, your chances of being struck in a single year are about 1 in 100,000, and about 1 in 3,000 over your whole lifetime. These odds can vary a lot depending on where you live and what your habits are, of course. Like if you live in Tampa and you like to play golf in July and you have no fear of storms, your odds of getting zapped are, yeah, you're stupid. But there are actually 2 different types of lightning strikes: direct and indirect. Direct is like Zeus aiming at the bullseye on the top of your head. It also occurs if you're holding on to something like a flagpole, for example, that is struck and it conducts the energy into you. Indirect strikes hit the ground and then run up your legs. More people are injured in ground strikes because the energy in them can connect to multiple people at once. So while the direct from above strike can hit a person in a crowd and leave everyone else alone, indirect strikes could kill a whole herd of cows in seconds. And yeah, a lightning strike is no joke. It's a 300 kilovolt burst of energy that can heat the air around it to 27,000 degrees Celsius, which is about 5 times hotter than the surface of the freaking sun. So, What exactly happens when the fire of 5 suns zips through your flesh and blood? Well, worst case, of course, you die. If the electrical current gets up in your skull, it can actually cook your brain like that famous egg in the anti-drug frying pan. But the most common immediate cause of death by lightning is cardiac arrest, as the shock instantly stops the strike victim's heart. Surprisingly though, 70 to 90% of lightning strike victims survive. I'm not saying they get back up and continue their game of golf unscathed, because the resulting injuries can be severe, but if you're struck, you're more likely to survive than just die there on the spot. And if you do survive, here's some of what you can expect. The force of the bolt leaving your feet could literally blow your shoes off. Meanwhile, the superheat of the strike could shred your clothing or set it on fire. And if you're wearing a lot of jewelry or, say, an underwire bra, that metal could channel the electrical current and sear your skin. The lightning bolt itself is probably going to leave deep wounds where it enters and exits your body, so you're gonna get burned. You might also end up with possibly the coolest scar on the planet. The unique physics of electrical discharge leaves branch-like marks called Lichtenberg scarring, which occur as blood vessels burst, and the bizarre fractal scars actually look like lightning. It's like getting a free souvenir tattoo. With that kind of electricity coursing through your body, you're also likely to end up with some damaged or totally fried nerves, which could lead to permanent numbness, the inability to register temperatures, or partial paralysis. Some strike survivors develop muscle twitches as well, similar to those in Parkinson's patients. Also, not technically an effect of the lightning, your eardrums might rupture from the thunder. For many strike survivors, it's actually the initial trauma that's the easiest part of the whole ordeal. The mental and physical after effects are often plentiful and bizarre. Memory loss, sleep disorders, tremors, loss of balance, intense headaches, chronic irritability, and resulting depression are all common side effects. Some of these symptoms may take months after the initial strike to manifest. Because being struck is so rare, many doctors don't know how to help their patients. This complaint, along with higher suicide rates in strike victims, has led to the formation of various lightning strike survivor support groups. Roy Sullivan holds the record for receiving the most lightning strikes. He was struck by lightning 7 times during his career in the Forest Service. But though he survived the strikes initially, they may have eventually killed him when he took his own life, likely due to depression caused by repeated shocks to his brain. Thanks for watching this SciShow Dose. If you have any questions or comments or ideas, we're on Facebook and Twitter and down in the comments below. And if you want to keep getting smarter with us here at SciShow, you can go to youtube.com/SciShow and subscribe.
So here's a little bit of graphic pictures. Apologize, I didn't warn you about this, of what it might look like when you get struck. So here's a forehead where the lightning entered his head, so extremely high electrical current. And then you can see the exit wound where the lightning exited out of the body through your feet into the ground. Now these Lichtenberg scars that he was talking about, here's some examples of them. And what happens is the electrical current, as it travels often along the surface of your skin, basically cauterizes the very fine blood vessels that are just underneath your skin and creates scar tissue. And you can see these very elaborate patterns that you can kind of envision, right? How the blood vessels are distributed in your skin, and also the path perhaps that the electrical charge took as it traveled through your skin. Now, how do you survive a lightning strike? Often you're told to get down as low as you can. That's true, but you don't actually want to lay on the ground. The best is to get in what they call a catcher's position. You don't want to touch anything metal, so you keep your golf club far away from you. If your hair starts to stand on end or starts to tingle, that's a sign that lightning may be about to strike. So you immediately want to get into the crouching position. You place your hands over your ears to protect them from the thunderclap. And the only thing you want touching the ground should just be the balls of your feet. Lightning can hit the ground first and then enter your body. So the more you minimize your contact with the ground, the less chance of electricity entering your body. That's the ground strike that he talked about here. It says, touch the heels of your feet together. If it enters your feet, it increases the chances that it may go in one foot and out the other and not travel through your body. If you're laying completely flat on the ground, then the lightning, if it's a ground strike, has many more places in which to enter your body. All right, that's our lesson for today. So we know how to define an electric field. We know how to calculate the electric field strength based on the electric charge and the forces between the charge that's creating the field and a test charge. And we can diagram an electric field by drawing the electric field lines. And we had an interesting look at how lightning works, the physics behind that, and how we can best avoid getting injured in a lightning storm. All right, that's it.